Flying at 3 times the speed of sound and reaching altitudes of 70,000 feet, the XB-70 Valkyrie stands as one of the most ambitious aircraft ever created. This remarkable supersonic bomber pushed the boundaries of aerospace engineering in the 1960s. The XB-70 Valkyrie combined revolutionary aerodynamics, advanced propulsion systems, and groundbreaking materials science into a single aircraft. Engineers equipped this massive bomber with 6 powerful engines, innovative delta wings, and a unique compression lift system that helped it achieve extraordinary speeds. The Valkyrie aircraft represented numerous technological breakthroughs, from its honeycomb panel construction to its sophisticated thermal management systems. This video will explore the exceptional engineering achievements that made the XB-70 bomber possible, examining its design features, propulsion systems, and the technical challenges the development team overcame to create this legendary aircraft. Revolutionary aerodynamic design features. The XB-70 Valkyrie's aerodynamic design represented a quantum leap in aircraft engineering, featuring innovations that would influence aerospace design for decades to come. The aircraft's distinctive delta wing configuration, combined with a canard surface, formed the foundation of its revolutionary design. The most notable feature was its compression lift system, which generated additional lift through an ingenious use of shock waves. At Mach 3 cruising speed, the shock wave bent back approximately 65 degrees, creating a pressure differential of 40 pounds per square foot under the aircraft. This innovative system contributed to 5% of the total lift, with some configurations achieving up to 30% increased effectiveness in lift generation. The XB-70 Valkyrie featured an extraordinary wingtip system that remains the largest movable aerodynamic structure ever incorporated into an aircraft design. These immense hinged sections, spanning more than 20 feet at their trailing edge, were engineered to pivot to 2 distinct positions depending on the aircraft's speed. At speeds ranging from 300 knots to Mach 1.4, the wingtips could be angled downward by 25 degrees. When the aircraft reached speeds exceeding Mach 1.4, the wingtips could be lowered further to a 65-degree angle, accommodating flight up to and beyond Mach 3. This innovative variable geometry design served a range of critical purposes. During takeoff, landing, and subsonic flight, the wingtips were kept in a horizontal position to optimize the aircraft's lift-to-drag ratio, ensuring efficient performance and stability. As the XB-70 transitioned into supersonic speeds, the downward-angled wingtips played a pivotal role in enhancing aerodynamic efficiency. By shifting the center of pressure and improving directional stability, this system significantly reduced trim drag, enabling the aircraft to maintain superior performance and control at extreme velocities. Perhaps the most innovative aspect of the XB-70's design was its ability to ride its shock wave, similar to a surfer riding an ocean wave. The aircraft's slab-sided fuselage and strategically positioned triangular intake created a controlled shock wave system. The shock wave generated by the leading edge of the engine intake splitter, positioned below the wing's apex, created a higher pressure zone beneath the aircraft. The design's effectiveness was proven during testing, as the second XB-70 achieved Mach 3 for the first time on January 3, 1966. However, this capability came with challenges. Tests revealed that the shock waves could generate significant overpressures, particularly during turns where converging shock waves could double the pressure on the ground. The integration of these aerodynamic features created a synergistic effect. The combination of compression lift, variable geometry wingtips, and shock wave riding capabilities allowed the XB-70 to maintain stable flight at speeds up to Mach 3.08 and altitudes of 74,000 feet. Propulsion system engineering. The propulsion system of the XB-70 Valkyrie represented a masterpiece of engineering innovation, combining raw power with sophisticated air management systems. The heart of the Valkyrie's propulsion system consisted of 6 General Electric UG 93 turbojet engines, each delivering 28,000 LEAF with afterburner and 19,900 LEAF without afterburner. These engines were housed in a unique slab-sided fuselage design, with the power plants arranged in a compact cluster formation. The engine configuration was specifically designed to handle the extreme conditions of sustained Mach 3 flight, where temperatures could reach 630 degrees. The XB-70 Valkyrie was equipped with an innovative advanced inlet system, a cutting-edge design that embodied the principles of aerodynamic precision and efficiency. This system employed a sophisticated multi-shock, variable area, convergent-divergent configuration that adapted seamlessly to the aircraft's varying flight conditions. It operated within 4 distinct regimes, each meticulously tailored to optimize performance across the full flight envelope. During takeoff and subsonic flight, up to speeds of Mach 0.6, the system functioned in low-speed mode. In this phase, the bypass doors remained completely closed and the throat panels were fully retracted, allowing for smooth airflow and efficient propulsion at low velocities. As the aircraft accelerated into the transonic range, from high subsonic speeds to Mach 1.1, the system transitioned into transonic mode. Here, the bypass doors remained closed, but the throat panels adjusted dynamically to manage the changing airflow demands. At speeds extending up to Mach 1.8, the system shifted into intermediate mode. During this phase, the bypass doors were fixed open by a predetermined increment, enabling enhanced airflow management necessary for the increased speed. For velocities exceeding Mach 1.8, the high-speed mode was engaged. This phase utilized modulated bypass doors, a feature designed to control shockwaves effectively and maintain optimal airflow alignment with the engines. The advanced inlet system continuously monitored and adjusted inlet and engine parameters to ensure maximum thrust and efficiency throughout every stage of flight. By harmonizing these elements, it achieved unparalleled performance, maintaining peak efficiency and enabling the XB-70 to excel across a broad range of operational conditions, from subsonic cruising to high-speed supersonic flight. The XB-70's fuel system incorporated innovative cooling solutions that were crucial for sustained high-speed flight. The aircraft utilized specialized jet fuel, formulated specifically for its unique mission requirements. Engineers developed an advanced fuel management system where fuel was pumped through heat exchangers before reaching the engines, effectively using the fuel as a coolant. The fuel system faced significant engineering challenges, particularly in maintaining proper sealing at extreme temperatures. The airframe's thermal expansion caused several inches of growth during flight, requiring specially designed fuel tank sealing solutions. Engineers implemented a fluorinated synthetic rubber called Viton B to address sealing challenges in the high-temperature environment. The propulsion system's effectiveness was demonstrated during testing when the second XB-70 achieved sustained Mach 3 flight for 32 minutes. This achievement validated the integrated design approach, showing that with a full fuel load, the aircraft could maintain Mach 3 flight for up to 2.5 hours. Materials science breakthroughs. The materials science achievements in the XB-70 Valkyrie program marked significant advancements in American industrial technology, particularly in steel manufacturing and structural engineering. The XB-70's construction featured an unprecedented application of stainless steel honeycomb paneling 22,000 square feet of the aircraft's surface. These panels consisted of thin stainless steel sheets brazed to a honeycomb-like core, creating a structure that was both lightweight and incredibly strong. The manufacturing process required exceptional precision, working with stainless steel just 0.02 inches thick. The material composition of the XB-70 Valkyrie was meticulously engineered to endure the extreme thermal conditions encountered during high-speed flight, particularly at Mach 3. This advanced design combined innovative materials and construction techniques to achieve exceptional heat resistance and structural integrity across the entire airframe. The primary structure of the aircraft was constructed using stainless steel honeycomb panels, a material chosen for its outstanding ability to dissipate heat effectively while maintaining lightweight durability. In critical areas subject to the highest thermal stresses, titanium components were employed, making up approximately 9% of the overall structure. The nose section, which faced the most intense aerodynamic heating during supersonic flight, was crafted from specialized titanium, providing unmatched thermal resistance and strength under extreme conditions. During sustained operations at Mach 3, the XB-70's materials showcased their remarkable thermal performance. The nose and horizontal splitter of the aircraft reached peak temperatures of 625 degrees Fahrenheit, while the majority of the skin maintained a more moderate temperature of around 450 degrees Fahrenheit. This effective thermal management not only preserved the structural integrity of the airframe, but also allowed the XB-70 to maintain superior operational efficiency and safety. Compared to other high-speed aircraft of its time, the XB-70's ability to withstand and manage such intense heat was unparalleled. Its advanced material composition and engineering ensured performance and durability far exceeding contemporary designs, cementing its reputation as one of the most innovative and resilient aircraft ever built. Engineers developed innovative solutions to address unique structural challenges. The brazing technique for assembling honeycomb structures represented a breakthrough in aircraft manufacturing. This method replaced traditional welding, which proved impossible with such thin materials. The engineering team also solved initial challenges with paint adhesion through the application of specialized thinner coats. The fuel tanks exemplified the sophisticated integration of structural and thermal management systems. These tanks served dual purposes, storing fuel and acting as heat sinks for temperature control. The system was so effective that it could maintain safe operating temperatures, even as the airframe expanded several inches during flight. To prevent fuel combustion at high temperatures, engineers implemented a nitrogen gas replacement system, as even a 2% oxygen presence could have caused catastrophic results. These materials science innovations contributed significantly to American industrial advancement, particularly in metallurgy and steel production. The successful implementation of these technologies demonstrated the feasibility of sustained high-speed flight using primarily steel construction, rather than relying exclusively on exotic materials. Control systems innovation. The sophisticated control systems of the XB-70 Valkyrie represented a breakthrough in aviation technology, incorporating advanced electronic and mechanical innovations to manage this extraordinary aircraft. The XB-70's flight control system featured a dual-channel mechanization with a unique force-summing servo arrangement. This sophisticated system blended pilot inputs with aircraft response sensors through specialized flight augmentation control system electronics. The system's architecture included a fail-soft mechanism that would lock the servo in case of channel disagreement, preventing unwanted surface movement. The control system of the XB-70 Valkyrie was a marvel of engineering, blending traditional hydromechanical mechanisms with cutting-edge electronic and servo-assisted technologies to achieve exceptional precision and responsiveness in flight. At its core, the system employed hydromechanical column-to-surface controls, which established a direct and reliable connection between the pilot's inputs and the aircraft's control surfaces. This foundational design ensured robust functionality and resilience, particularly during high-stress flight conditions. To enhance maneuverability and stability, the system was augmented with a dual-channel electronic system. This electronic augmentation provided real-time adjustments to the control surfaces, compensating for aerodynamic disturbances and optimizing the aircraft's handling characteristics across its wide flight envelope, from subsonic speeds to Mach 3. Additionally, advanced mechanical servo systems were integrated into the control architecture. These servos amplified the pilot's inputs, allowing for precise control of the aircraft's massive and complex control surfaces with minimal physical effort. This integration of hydromechanical and electronic systems with servo assistance enabled the XB-70 to achieve an unprecedented level of control and stability, crucial for its role as a high-speed, high-altitude bomber. The sophisticated interplay of these technologies not only enhanced the piloty to manage the aircraft with ease, but also contributed significantly to the XB-70's reputation as a groundbreaking achievement in aerospace design. The Valkyrie pioneered revolutionary stability control through the identically located acceleration and force experiment. Two small vanes were installed that could rotate 12 degrees at up to 8 cycles per second. This system generated controlled structural vibrations at specific frequencies and amplitudes, while accelerometers detected these disturbances and signaled the stability augmentation system to dampen the motion. The stability system proved particularly effective in reducing the effects of turbulence, minimizing atmospheric temperature impact, and improving overall flight stability. The cockpit integration represented a significant advancement in human-machine interface design. A specialized rate of climb meter, adapted from helicopter technology, was installed to assist pilots in maintaining precise control. The system included an innovative windshield design featuring a lowerable outer section and ramp, enabling improved visibility during high-angle flight operations while maintaining aerodynamic efficiency at high speeds. The control system's effectiveness was demonstrated when the second XB-70 achieved Mach 3 flight in January 1966. However, the prototype experienced stability challenges beyond Mach 2.5, leading to operational limitations. These challenges prompted continuous refinement of the control systems, resulting in improved handling characteristics and more reliable performance at high speeds. The integration of these control innovations proved crucial during research flights, where pilots frequently encountered trim changes and buffeting during high-speed, high-altitude operations. The sophisticated control systems help manage these challenges, enabling the aircraft to maintain stable flight even under extreme conditions. Thermal management solutions. Managing extreme temperatures posed one of the greatest engineering challenges in the XB-70 Valkyrie's development. The aircraft's ability to sustain Mach 3 flight demanded innovative solutions for handling intense thermal loads. The XB-70 Valkyrie's heat management system was a testament to advanced aerospace engineering, meticulously designed to withstand the extreme temperature variations generated during high-speed flight. At Mach 3 cruise, the aircraft encountered intense thermal conditions across its airframe, with average skin temperatures reaching approximately 450 degrees. The leading edges of the wings and other forward-facing surfaces, subjected to the brunt of aerodynamic heating, soared to around 630 degrees. Meanwhile, the engine compartments endured the most severe heat, with temperatures climbing as high as 1000 degrees. To address these formidable thermal challenges, the XB-70's design incorporated strategic heat management solutions throughout its structure. Material selection played a critical role, with stainless steel honeycomb panels and titanium components chosen for their superior thermal resistance and ability to dissipate heat effectively. The nose section, frequently exposed to the highest temperatures, was engineered with specialized titanium construction, ensuring durability and thermal stability under extreme conditions. Engine compartments require even more intricate solutions due to their exposure to both aerodynamic heating and the heat generated by the propulsion system itself. Engineers developed innovative structural designs and thermal barriers to manage and distribute heat loads effectively, preventing localized overheating and preserving the integrity of the surrounding materials. This comprehensive approach to heat management enabled the XB-70 to maintain structural integrity and performance throughout its high-speed flight envelope. The system not only protected the aircraft from thermal stress, but also set a new benchmark in aerospace engineering, demonstrating an unparalleled ability to manage extreme heat in supersonic aviation. The XB-70's cooling system utilized an ingenious approach that turned necessity into an advantage. The fuel system served a dual purpose as both a power source and a cooling medium. Engineers designed a sophisticated network of heat exchangers through which fuel circulated en route to the engines. This system effectively absorbed heat from the airframe before the fuel reached the combustion chambers. The cooling system required precise management of fuel temperatures and flow rates. To prevent fuel ignition in the tanks, engineers implemented a nitrogen gas pressurization system. This safety measure was crucial, as even a 2% oxygen presence in the fuel tanks could have resulted in combustion due to the extreme temperatures. The thermal management strategy relied heavily on advanced materials with specific heat-resistant properties. The aircraft's structure utilized a combination of materials selected for their thermal characteristics. The stainless steel honeycomb panels, which formed the majority of the aircraft's exterior, provided excellent heat dissipation properties. These panels consisted of two thin sheets of stainless steel brazed to a honeycomb-shaped core, creating an effective thermal management structure that was both lightweight and strong. In areas experiencing the highest temperatures, such as the nose structure, engineers employed titanium components. This metal's superior thermal resistance properties made it ideal for these critical sections, despite its challenging manufacturing characteristics. The combination of these materials created an effective thermal management system that allowed the XB-70 to maintain structural integrity during sustained high-speed flight. The effectiveness of these thermal management solutions was demonstrated during test flights, where the aircraft maintained structural integrity despite the extreme temperatures encountered during Mach 3 operations. The system's success represented a significant advancement in aircraft thermal management technology, establishing new standards for high-speed flight operations. Engineering challenges overcome. Throughout the development of the XB-70 Valkyrie, engineers confronted and conquered numerous technical obstacles that pushed the boundaries of aerospace technology. Their innovative solutions established new benchmarks in aircraft design and construction. The initial XB-70 prototype revealed significant directional stability challenges during high-speed flight. The first aircraft demonstrated poor stability above Mach 2.5, limiting its operational capabilities. Engineers at NASA Ames Research Center tackled this problem through extensive wind tunnel studies, leading to a crucial modification, adding 5 degrees of dihedral to the wings of the second XB-70. This adjustment proved highly successful, enabling the aircraft to achieve Mach 3.08. To tackle the challenges of stability inherent in high-speed flight, the development team of the XB-70 Valkyrie devised an innovative solution through its adjustable wingtip configurations. These movable wingtips were a groundbreaking feature, designed to enhance aerodynamic efficiency and directional stability across a wide range of speeds. At speeds up to Mach 1.4, the wingtips could be angled downward by 25 degrees. This configuration optimized the aircraft's performance in the transonic regime, improving stability while minimizing drag. As the XB-70 accelerated beyond Mach 1.4, the wingtips could be further adjusted to a 65-degree downward angle. This more extreme configuration was critical for maintaining directional stability and reducing trim drag during sustained supersonic flight, particularly at speeds approaching Mach 3. These variable wingtip settings not only allowed the XB-70 to adapt to different flight conditions, but also played a crucial role in managing the shift in the center of pressure that occurs at high speeds. By dynamically altering the aircraft's aerodynamic profile, the wingtips contributed to the XB-70's ability to achieve unparalleled performance stability, underscoring the ingenuity and precision of its design. One of the most significant challenges involved managing structural expansion at high temperatures. The fuselage panels were deliberately manufactured to fit loosely on the ground, as the airframe would expand several inches during flight. This design accommodation required precise engineering calculations to ensure proper alignment at operational temperatures. The engineering team faced the critical challenge of ensuring fuel tank integrity under extreme operating conditions. To address the risks of leaks and maintain performance, they developed specialized sealing solutions tailored to withstand the aircraft's demanding thermal and aerodynamic environment. One key innovation was the application of a fluorinated synthetic rubber known as Viton B. This material was specifically used to coat porous areas of the fuel tanks, providing a robust barrier against leaks while offering exceptional resistance to fuel exposure and high temperatures. Its chemical stability ensured reliable performance even under the extreme thermal stresses experienced during Mach 3 flight. In addition to this coating, the team employed advanced brazing techniques to reinforce tank seams and joints. This method created durable, leak-proof connections between components, capable of enduring the intense vibration and pressure fluctuations associated with high-speed operations. To further enhance sealing, specialized organic sealants were incorporated into the design. These sealants were engineered to withstand temperatures as high as 600 deg, making them particularly effective in high heat zones, such as those near the engines and leading edges. Their heat-resistant properties provided an additional layer of protection, ensuring the fuel system's integrity throughout the aircraft's flight envelope. These innovative sealing methods exemplified the meticulous attention to detail in the XB-70's design, enabling it to operate safely and efficiently at unprecedented speeds and altitudes. The integration of multiple complex systems presented unique challenges. Early flight tests revealed issues with paint adhesion, which engineers resolved by applying thinner coating layers. The fuel system required particular attention due to the extreme operating conditions. Engineers developed an innovative approach using fuel as a coolant, pumping it through heat exchangers before reaching the engines. Clear air turbulence and rapid temperature changes during high-speed, high-altitude flights created additional complications. The development team addressed these issues through the implementation of the identically located acceleration and force experiment. This system utilized small vanes rotating at up to 8 cycles per second to counteract turbulence effects. The XB-70's development yielded over 1,000 patents and thousands of technical innovations. Each challenge overcome contributed to the advancement of aerospace engineering, from materials science to control systems. The solutions developed for the Valkyrie program influenced aircraft design for decades to come, particularly in areas of high-speed flight and thermal management. Performance testing results. Extensive flight testing of the XB-70 Valkyrie yielded remarkable performance data that validated many of its groundbreaking design features while revealing important insights about high-speed flight. The XB-70's flight testing program demonstrated exceptional performance capabilities. The first prototype achieved Mach 3.02 on October 14, 1965, while the second prototype, AV2, reached Mach 3.5 at 70,000 feet on January 3, 1966. The XB-70 Valkyrie achieved remarkable operational performance, showcasing its advanced engineering and capability. Its maximum speed reached an impressive 2,056 miles per hour, equivalent to Mach 3.1, while flying at an altitude of 73,000 feet. During sustained operations, the aircraft maintained a cruising speed of 2,000 miles per hour, or Mach 3.0, at an altitude of 72,000 feet. The Valkyrie's service ceiling extended to 77,350 feet. With a range of 4,288 miles, it demonstrated significant endurance, suitable for long-range missions. Additionally, the aircraft exhibited a rapid rate of climb, ascending at 7,170 feet per minute. The XB-70 Valkyrie's handling characteristics shifted dramatically depending on its position within the flight envelope, presenting both challenges and unique phenomena during operation. At high speeds and altitudes, the aircraft's performance was influenced by several significant factors. Pilots frequently encountered the effects of clear air turbulence, which necessitated constant trim adjustments and resulted in noticeable buffeting. These disturbances required careful control inputs to maintain stability and optimize performance under turbulent conditions. As the aircraft transitioned through different atmospheric pressure zones, instruments such as the altimeter and rate of climb indicators displayed notable fluctuations. These variations reflected the dynamic pressure fields at high altitudes and speeds, demanding heightened situational awareness from the flight crew. Additionally, the prototype of the XB-70 exhibited a marked deficiency in directional stability at speeds exceeding Mach 2.5, a challenge that highlighted the complexity of maintaining control at extreme velocities. Despite these challenges, the XB-70 demonstrated exceptional aerodynamic versatility in its lift coefficients across various flight phases. During cruise conditions, lift coefficients ranged from 0.1 to 0.13, ensuring efficient performance at supersonic speeds. For takeoff, the aircraft's lift coefficients ranged between 1.3 and 0.73, facilitating the generation of sufficient lift for departure. Similarly, during landing, the lift coefficient stabilized at 0.626, balancing the need for control and descent stability. These adaptable lift characteristics underscored the Valkyrie's sophisticated aerodynamic design, allowing it to perform effectively across its demanding operational spectrum. The comprehensive flight test program generated valuable reliability data across multiple systems. Between 1964 and 1969, the two XB-70 prototypes completed 129 flights, accumulating 252 hours and 38 minutes of total flight time. The second prototype demonstrated superior reliability, completing 9 Mach 3 flights before June 1966. Test data revealed significant findings about the aircraft's aerodynamic efficiency. The testing program revealed critical insights about sonic boom characteristics. When the XB-70 executed turns, its shock waves converged, often doubling the overpressure on the ground. This discovery proved valuable for understanding high-speed flight environmental impacts. The aircraft's sophisticated systems demonstrated remarkable reliability during extended high-speed cruise. The second XB-70 achieved a sustained 32-minute Mach 3 flight in May 1966, validating the effectiveness of its thermal management and propulsion systems. NASA's research program utilized the XB-70 to study various aspects of supersonic transport operations, including aircraft noise, operational challenges, and control system performance. The data collected significantly influenced future supersonic aircraft design, particularly in areas of stability augmentation and thermal management. Technical legacy impact. Despite its limited production run, the XB-70 Valkyrie's technological innovations continue to shape modern aerospace engineering, establishing benchmarks in aircraft design and materials science that resonate decades after its final flight. The XB-70's aerodynamic innovations laid the groundwork for subsequent aircraft developments. Its compression lift system, which generated an additional pressure of 40 pounds per square foot under the aircraft, influenced the design of future supersonic aircraft. The aircraft's remarkable lift-to-drag ratio remains unmatched among manned aircraft, surpassed only by the unmanned D-21 drone. The Valkyrie's research program significantly impacted American supersonic transport efforts. NASA utilized the aircraft as its primary testbed for SST operations, gathering crucial data about sonic boom characteristics and ground effects, high-speed flight dynamics, thermal management solutions, and stability control systems. The XB-70's materials science achievements sparked significant advances in American industrial technology, particularly in steel manufacturing. The program's innovative use of stainless steel honeycomb panels, covering 22,000 square feet of the aircraft's surface, revolutionized aircraft construction techniques. The development of specialized brazing techniques for assembling honeycomb structures represented a significant breakthrough in aircraft manufacturing. These innovations led to advances in metallurgy and steel production that extended beyond aerospace applications. The XB-70 program was a remarkable source of innovation, resulting in over 1,000 patents and numerous technological advancements that significantly advanced the understanding of high-speed flight operations. The program provided critical engineering insights by addressing a range of challenges in thermal management, stability control, and systems integration. In the realm of thermal management, the aircraft's ability to maintain skin temperatures of just 450 degrees Fahrenheit during a Mach 3 flight was a groundbreaking achievement. This was made possible through strategic design choices, such as utilizing fuel tanks as heat sinks for equipment placement, an approach that proved highly effective in dissipating heat. Additionally, innovative cooling systems demonstrated the feasibility of sustained high-speed operations, setting a new benchmark for future supersonic aircraft. The program also made significant strides in stability control, particularly through the identically located acceleration and force experiment. This effort provided invaluable data on managing the effects of clear air turbulence and atmospheric temperature variations, leading to advancements in stability systems that influenced the design of future aircraft. In systems integration, the XB-70 highlighted the importance of cohesive design approaches. A key innovation was the engine installation system, which allowed complete engine replacements to be carried out within hours instead of days. The XB-70's research flights revealed critical insights about supersonic transport operations. Tests showed that large aircraft could generate significant overpressures, with shock waves doubling during turns. These findings proved invaluable for understanding the environmental impact of supersonic flight. The aircraft's design influenced subsequent developments in military aviation, including elements incorporated into the B-1 Billion Lancer bomber and Su-71 Blackbird reconnaissance aircraft. Its advanced delta wing configuration and unique compression lift system continue to inform modern supersonic aircraft design. The program's achievements in materials science and thermal management remain relevant to contemporary aerospace challenges. The successful implementation of stainless steel honeycomb construction demonstrated that innovative engineering could achieve high performance without exclusive reliance on exotic materials. NASA's research program utilizing the XB-70 generated valuable data about supersonic transport operations, including aircraft noise characteristics, operational challenges, and control system performance. These findings continue to influence the development of modern high-speed aircraft, particularly in areas of stability augmentation and thermal management. The XB-70 Valkyrie is a symbol of American aerospace innovation, achieving Mach 3 flight with groundbreaking technologies in compression lift, thermal management, and materials science. Over 129 test flights, the program validated numerous advancements, from its honeycomb panel construction to its innovative propulsion and control systems. The Valkyrie also provided crucial insights into supersonic flight, particularly regarding sonic boom and thermal management, and its innovations extended beyond aviation into other industries. Its legacy continues to impact aircraft design, representing the peak of 1960s aerospace engineering. What do you think was the most impressive feature of the XB-70 Valkyrie? Please share with us in the comment section of the video. Thanks for watching. See you in the next videos.